Hello, my name is Niru Sundara. My metric number is 22004515, and this is my video presentation for the Machine Learning Final Exam Part 2. In this video, I'll be walking through my methodologies, my architectural decisions, and my analytical findings for the modeling task performed in Part 1, covering both the gas turbine emissions dataset and the superconductor dataset. And let's begin with question 1. For the first question, I developed a stacking enabled model to predict gas turbine emissions. The foundation of this model consists of 3 diverse base learners, a decision tree regressor limited to a max depth of 4 to prevent overfitting, a random forest regressor using 100 estimators to reduce the variance through bagging, and a gradient boosting regressor with 300 estimators and a learning rate of 0.05 and a max depth of 4 to sequentially correct residual errors. For the meta learner, I chose a simple linear regression model. The data flow within this architecture works in 2 stages. First, the original training data is fed into the 3 base learners. These 3 base learners generate their own predictions for the target variable. These decisions are then concentrated to form a completely new feature matrix. The linear regression meta learner then uses a new matrix as an input to predict the final output. This approach improves the performance because the meta learner essentially learns the strengths and weaknesses of each base model. If the decision tree overestimates a certain region, but the gradient booster is highly accurate, the meta learner will assist the higher weight to the gradient booster's prediction, yielding a more robust final output. During the development of this model, I encountered a real issue with overfitting. Initially, if a stacking model is trained without proper cross-validation, the meta learner will simply memorize the base state model's training prediction and learning to an artificially low training error, but terrible generalization on unseen test data. I identified this issue when my preliminary validation metric shows a massive gap compared to my training metrics. This address, I explicitly utilized the CV equals 5 parameter inside the skillet learn stacking regressor. This ensures that the meta features are generated using out-of-fold prediction, meaning the meta learner is strictly trained on a data where the database models have never seen, successfully eliminating the data leakage and overfitting. Moving to question 2, I analyzed the high-dimensional superconductor dataset. I applied principal component analysis and selected 17 principal components. I made this decision by plotting the cumulative explained variance ratio against the number of components. The plot revealed that 17 components were required to retain exactly 95% of the total variance in the dataset. This threshold drastically reduces the dimensionality from 81 features to 17, keeping the vast majority of the information signals. However, when comparing the ANN trained to the PCA data versus the original dataset, the results were surprising. The AN without PCA actually performed better, achieving a R-squared of 0.886 compared to the PCA model of 0.869, and the lower mean absolute error of 7.30 versus the other one, which is 8.01. In terms of training stability, the validation losses curve showed that the original dataset model had a smoother, more stable descent, whereas the PCA model exhibit more jagged fluctuation, indicating slight instability. Neither model severely overfitted thanks to the early stopping callback implemented. Therefore, in this case, PCA did not improve the model's performance. The justification lies in the dataset's characteristics. The superconductor is governed by high, complex, non-linear quantum and chemical interactions. PCA is strictly for linear transformation. By discarding 5% of the variance, we permanently erase subtle non-linear physical nuances, and the full neuron network, which natively handles non-linear district, was able to map those subtle nuisances into better predictions when given the raw data. Regarding to the network architecture, I designed a funnel structure, input layer followed by two hidden layers of 64 and 32 neurons, and a single neuron output layer. I use ReLU activation function to hide the layers because it computationally efficient and efficiently mitigates the vanishing gradient problem in deep networks. If I were to retain the model and with a different number of PCA components, for example, compressing it down to only maybe 5 components, I would thusly simplify the ANN architecture, reducing it to a single layer of maybe 16 neurons. A massive network processing too many components would have vastly more parameters than necessary, leading to a rapid memorized noise and overfit. Finally, for question 3, I will be highlighting the findings from the gas turbine data in part 1. During the exploratory data analysis, I identified that the feature TIT, which stands for turbine inlet temperature, had a significant influence on the model for predicting carbon monoxide emissions. I identified this using the PANDAS correlation metric, which statistically revealed a massive negative Pearson's correlation of negative 0.071 between TIT and CO. This physical relationship indicates that running the turbine at hotter temperature results in a significant cleaner CO burn, making it most critical predictive feature for the models. A vital pre-processing decision that I made to support this was applying a standardization using the standard scaler on the feature matrix before modeling. This decision had a profound impact on model performance. The dataset contained features with vastly different scales. For instance, the turbine inlet temperature operates in 1,000 of degrees, while the air filter different pressure operates in single digits. Without standardizing, distance-based and gradient descent-based models would mathematically treat the temperature as vastly more important simply because of the sheer numerical magnitude, leading to heavy bias gradients, slower convergence, and also degraded accuracy. If I were to be given a similar dataset but with a significantly larger number of features, say 1,000 of sensors reading, my approach would change heavily towards dimensionality reduction. I would implement strictly L1 lasso regulations for feature selection, or apply PCA before training to eliminate the curse of dimensionality and prevent the model from overfitting to noise. Conversely, if the data set had a very small number of features, I would avoid aggressive reduction techniques. Instead, I would simply rely on models like standard decision trees and also focus on manual feature engineering, such as creating polynomial combinations to extract as much predictive power from the limited variables as possible. That concludes my analysis and explanation for the part 2 of the final examination. Thank you so much for your time, and thank you for a great semester. Bye bye.